Swayam Prabha. Digital India. Educated India.
Now, having seen this, next let us move on to thermal stresses. Okay. So, I have the same step shaft. Okay. I have the same step shaft A, B, C, 2A, E, area of cross section A, Young's modulus E, this length is 2L and this length is L. This is problem 5. Okay. This I am subjecting to a rise in temperature of delta theta. Structure ABC sees a rise in temperature of delta theta and the coefficient of thermal expansion is alpha for both. The coefficient of thermal expansion is alpha. Find the stress in member AB and BC. Okay. Now, how will you solve this problem? There is no applied force here, just the temperature of the structure increases by delta theta. Okay. Apart from the stress, I want to find also the displacement, find also the displacement of the section B. Okay. I want to see by how much this section B moves and I want to find what will be the stresses in member A, B and B, C. Okay. Now, what can you say? When temperature rises, A is fixed, so it cannot move, B will move by say delta B, B moves by delta B, this is A B, B C, B moves by delta B and C moves by delta C. Okay. There is no force applied. So, what will be the observed strain? Observed strain would be delta B by 2L, the length of the member. This will be equal to epsilon mechanical strain plus alpha delta theta, which is the thermal strain along the direction, axial direction for AB. Okay. This is mechanical strain in member AB. Similarly, for BC, the strain would be delta C minus delta B by L, that is coming from a strain displacement relationship. B moves by delta B, C moves by delta C. So, the strain would be the difference between the displacement of C and B. Okay. So, that is delta C minus delta B by the length of the member, which is L. Okay. This will be equal to the mechanical strain in BC plus alpha delta theta, which is again the strain in member BC due to thermal effects. Okay. Now, since there is no force applied in AB, what will be the mechanical strain AB? Mechanical strain AB from the constellation would be the stress in AB by the Young's modulus E. Since there is no force applied in member AB, the stress is going to be 0. Okay. Similarly, the mechanical strain in member BC would be the stress in BC by the Young's modulus. I am applying no force in this member BC. So, the stress in member BC would be 0 and this will also be 0. From this I get delta B to be equal to 2 alpha delta theta into L, and delta C would be delta B plus alpha delta theta to L, which will be 3 alpha delta theta into L, that is delta C. Okay. That is, the change in cross section does not matter, the total length of the member is 3L. So, the elongation at point C would be 3L times alpha delta theta. Okay. Now, let us solve the final problem of this lecture, which will be problem number 6. It is the same as problem 5, except that I have a restraint at C. Just like in problem 3, I have this distance given by delta, this is A, B, C, this has 2A as area of cross section, E as the Young's modulus, alpha as the coefficient of thermal expansion, A, E, alpha for BC, this has a length 2L and this has a length of L, BC has length of L. Okay. Now, I eat it. Now, what will happen until delta the temperature change is such that the total elongation of the member is delta, there will not be any force coming in, it will be same as problem 5. Okay, it will be same as problem 5. Now, after the gap closes, there will be mechanical stresses arising, because there will be a compressive stress coming at compressive force coming at C, which will propagate and it will change the entire dynamics of the problem. Okay. So, basically how do you solve this problem? You assume again as we did in problem 3 that the gap is closed due to a change in temperature, okay, and then what you do is you draw the free body diagram. AB, BC, there is say a compressive force F applied here, there arises another compressive force F, there will be by continuity at B, there should be a compressive force F here and F here too. Okay. So, since there I assumed F over here and I do not know what this F is, I have to find the F such that the displacement of point C is delta, to find F such that the displacement of point C is delta and not more than delta. Okay. So, now again I write the same equations, I assume delta B moves by, this moves by delta B, this moves by delta B and this moves by delta C. Same things I write as before, this observed strain in member AB is delta B by L by 2L, that will be equal to the mechanical strain in AB plus alpha delta theta. Similarly, the observed strain in member BC would be delta C minus delta B by L, which will be equal to the mechanical strain in BC plus alpha delta theta. Okay. Now, the mechanical strain in member AB would be minus F into minus F by 2A E. Okay. That will be the mechanical strain in member AB. F by A is the stress in member AB, the stress by strain. F by 2A will be the strain in member AB. F by 2A will be the stress in member AB, and that stress divided by the Young's modulus will give me the strain in member AB. Similarly, the mechanical strain in BC is given by F by A into 1 by E, the stress in member BC divided by the Young's modulus of member BC. Okay. Now, substituting this back in there, I get delta B to be minus F by AE into L plus 2L alpha delta theta, and I get delta C to be delta B plus F L by AE minus FL by AE plus alpha delta theta into L. Okay. Substituting for delta B, this will be minus 2 FL by AE plus 3 alpha delta theta into L would be delta C. We know from the comparability condition that the displacement of point C cannot exceed delta. So, this will be equated to delta, and from this equation we obtain F as 3 alpha delta theta into L minus delta AE by L. From this you get F as 3 alpha delta theta minus delta into AE by 2 delta by L. Okay. We will get F as that, and from here it is clear that if delta is less than 3 alpha delta theta into L, then F would be positive, and that is the case that we want. If F becomes negative, then what happens is it is not possible. There cannot be a tensile stress in member BC. When the temperature increases, the members can be only in compression and it cannot be in tension. Okay. So, you from the physical argument you see that delta has to be less than 3 alpha delta theta into L, and then that is a condition when F will be greater than 0. If F were to be less than 0, if delta were to be less than 3 alpha delta theta into L, then the force F would be less than 0, not possible physically. Possible physically, hence limit F to be equal to 0. Okay. So, that is how you solve this problem. Okay. Just like what we did for problem 3, same arguments here to solve for problem 6. Okay. So, what you have seen in today's class is some 6 different boundary value problems involving axial members. The first three were of the same type, wherein you had only force applied on a homogeneous bar, but which had different cross sectional areas. In problem 4, we saw a bar which is inhomogeneous, made of 2 different materials, and in problem 5 and 6 we looked at the effect of thermal strains, or what is the effect of change in temperature on these structures. Okay. Thank you.